This is a simulation of single phase inverter using sinusoidal pulse width modulation, and unipolar switching technique is used. And here we are going to have the simulation run and we will see that how this is working. And here is a switch. Here the switch is named as S1. This switch can be named as one MOSFET. Here we can say S1. And you have another is S2 over here. Similarly, you have S3. The switch over here is S3. And this switch is S4. So you have here S1, S2 and S3, S4. So when S1 and S4 are turned on and off, depending on the sine and the triangular wave, when sine is greater than the triangular, we will have a pulse P1, and when sine is less than the triangular, we have a pulse P2 here. Similarly, another leg is there, S3 and S2, where S3 and S2 will be controlled by the another sine and triangular wave. The difference between this sine and this sine is just they are 180 degree out of phase, and the triangular is a carrier signal. There is no phase difference between them. And here also, when sine is greater than the triangular wave, we will get a pulse P3. When sine is less than the triangular wave, we have a pulse P2. So in this way, this is formed, and what we want to see in the first go, let us see this sine wave and another sine wave. So these two sine waves we are going to see simultaneously, and a carrier signal also we want to see simultaneously, so that we will have three signals together, but not this one. This one we would like to see the third one here. So this is these three are merged together to see in one way, and here we can see the P1 one pulse, and also we would like to see the pulse P3 in these things here. And the output here in this scope, we are going to see the output current waveform and the voltage waveform. The RL load is considered, that is 10 ohms and 0.01 Henry, and supply voltage is given 100 volt, just a normal 100 volts. So what is the output voltage and TSD we are getting? And in triangular wave, what we have done is we have generated the triangular wave by giving a gate pulse over here. Two gate pulses are given and they are added up. They are 180 degree out of phase, and then they are integrated. So we get an integration. So with the square wave +1 to -1, then we integrate it and add a -1, so that it will be normal. It will be biased between 1 and -1. And we would like to simulate it up to 0.1 seconds, so that will be enough. So but before that, we have to give some run this program. This is a program where the variables like what is the frequency is 50 Hertz and the modulating frequency is 13. So it is very difficult to understand directly from that. So let us say 5, which is not practically used, but let us say 5. And the switching frequency is 5 times of the fundamental frequency. Now we have done it, and here we are going to run this simulation. After running this simulation, we will see that what is the output voltages across the load, and what are the gate pulses that we both will see here. So simulation is run right now. So let us see the pulses first, and if the pulses are correct, that means the output, these signals will be correct. So if I run the pulses, so to understand the pulses, before that this is P1 is here in this leg, and P4 is that here in this leg, and they will definitely be out of phase. And what is of interest is that P3 and P2 is also out of phase, and at one time when P1 and P2 is switching on, like in first half P1 and P2 will be switching on, and another half P3 and P4 will be switching on. We are going to describe, understand later. So here the pulse is there, so let me zoom it up to some 2 cycles, let us say. So we zoomed it up to 1.5 cycle, 0.03. So if I zoom it to 1 cycle, it will be more clear. Okay, 1 cycle, and modulating frequency is 5, so there are 5 triangular wave in 1 cycle of sinusoidal, and these 2 sine waves are 180 degree out of phase, and the pulses are there. We get our pulses P1 when this black is greater than the triangular wave, then we're getting the pulse. You can see that when black is greater than the triangular, we're getting a pulse. When black is greater than triangular, we're getting a pulse like that. And we're getting another pulses, that is P3 here, when this blue line is greater than this blue line is greater than the blue line is greater than the triangular. Then see here, this is the reason when blue line is greater, here blue line is greater, here blue line is greater, here. So what I will do is just like it changing the style of that so that this will be a little bit this black line, you can see it is much bold. And let's see what we can do is sine waves. So here we have 2 waves, so this one we also like to see the bold one, and triangular one also we would like to see the bold. So let us apply. So now it is quite clear and visible. So another one we would like to see the second, let us make it a black, so because it is comparing and giving the black output, right? Another one we will give it a blue. So this is okay, this is blue, fine. So this is what we get, a blue one. So this is just color visibility, nothing else. So this is what we get the comparison of sine triangle. You can see that sine wave is the maximum magnitude is 0.8, and this is how we can see that we can just see the sine wave. This is the amplitude is taken 0.8, so that is why it is modulation index is 0.8 and modulating frequency is 5. So now let us see this output voltage and current waveform also. Here the current waveform and the voltage waveform. So from the voltage waveform, it is very clear that this is actually unipolar, because the output voltage is changing from 0 to 100 and 100 to 0, and in this way there is a change in the output voltage. And here it is 0 and minus 100. This is change what we observed in the output here. So overall this is 1 cycle from here to here. That is that we can see that this is our 1 cycle. So let me just zoom up 1 cycle only. So this is 0.01 is 180 degree, and if this is 0.05, this is 90 degree. So till 90 in quarter wave we are getting how many switchings? 1, 2, 3, 4, 5. So we are getting 5 switchings in the quarter wave. That's a point to be understand. The 5 switching is, if I using some other techniques, so I can define the alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. So 5 switching is there till this. Another very important thing that is to be understand is that what are the FFT analysis of this output voltage waveform. So for that we have to run a program like p equal to out.scope.data1. So there now we can run the FFT analysis of the output voltage waveform, which if we run, we get FFT here, and in this FFT analysis we can all get what is the output FFT analysis of that. So here we will get the output voltage and the current waveform of the scope data, which is stored in the scope over here. So this is a P is a variable that we choose. Number of cycles, let us say we would like to go for all the cycles to see that what is the output, and 50 Hertz is the frequency, and up to 4000 Hertz we want to see the harmonics, and then this is the current waveform and the voltage waveform is this. If we do the FFT analysis, we will get here the output over here. And enlarge this also. So here we are supposed to get that compute FFT. Yeah, FFT is here. And now we can zoom it in minus over here. So if we zoom, we can just see that fundamental will be zoom maximum is 100% is a fundamental. So we have given a 100 volt DC and we taken a modulation index as 0.8, so it's 80 volts. So instead of 80s, because of some drop in the switches, we are getting 79.38, and the total harmonic distortion is 78.88%. And this is that what we have got. The harmonics is okay. Let me have to brush it. That these are the in red color. Right, these are the harmonics. So we have taken the modulating frequency as 5, and 5 into 2 is the 10, and 10 minus 1 is this is the harmonics. 9th is a harmonic, then 7th is a harmonic, then we get a 7th harmonic and 9th harmonic. That is the way. And what is not there is 3 and 5 is not there. So 3 and 5, these two are not there. So we can save it, this data here also, save, and we can save this in this by mentioning the save as unipolar SHE, and we can keep it what is the modulating frequency is equal to 5. This is the what we have. We should keep it safe for our project report. So now what we will do is some changes over here is that we will do the modulating frequency. Instead of 5, we will take 6. If it's 6, then what? How does it give the change in the output here? So with modulating frequency 6, we are going to run this simulation once again. So this is the I've taken with modulating frequency 6. We run the simulation again, and we will see the results here in the output voltage. So instead of seeing the result, we will directly go for the FFT analysis of it. So for FFT, we have to just give a command and store the variables in p variable. Store the results in the p variable. Then we can double click on the discrete and FFT analysis, and here in the FFT analysis we can see that what is the voltage waveform. Again, number of cycles to be seen is 5, then frequency is 50, this is 4, and then we have Nyquist frequency is the frequency that up to which we will see the harmonics, and here we will want to see the output voltage. So if you run, you'll get the harmonic FFT analysis over here. So that's it for what we are going to get here. So now since we have taken a modulating frequency is 6, so here 6 into 2 is a 12. So 12 sideband is 11 and 13. So 11 we get, and this is 9. So 11 and 9 we get. The other harmonics is not there. That's what we get. And modulating frequency is modulating index is 8. So we should get 80. So we're getting 78.59. TSD is around 79.94. That's the TSD value. So here also we can save this by simply putting a minus, then we can zoom it up. Fundamental is reflected here, so we can just brush it up, this portion of it. So these are the harmonics, and then we can save this in a drive somewhere, then we can give it, name it like unipolar SPWM with a modulating frequency equals to 6 FFT. That is how we save it, and we can just save these pictures over there. Now another important thing that we can do the analysis of that is, if we see the waveform, the output waveform, and we see only the one cycle, and at 0.01 it is 180 degree, and 0.05 here is 90 degrees. So how many switching we have seen? 1, 2, 3, 4, 5, 6. So we are getting 6 switching in the quarter wave. 6 switching is actually 3 cycles. Also because 1, 2, 2 switching is that you are starting with 0 and again 0, then starting with 0 again you get 0. So like 6 switchings in quarter cycle. So 3 waves. So 3, 3, 6, 6 plus 6, 12. 12 cycles we are getting. So 6 modulating frequency is equal to 6. That also means 6 switching in quarter cycle. 6 alpha 1, alpha 2 up to alpha 6 will be there. Alpha 6, and here it is 90 degree. So this is what we get in the output. So that's the information we get and understand, and these are the same, the pulses, so which we can understand this. If we see only one cycle, there are 6 triangular waves in one cycle, and with this black one, when compared with the black we get this pulse, that is a P1. When compared with the blue we get another pulse, and in this way we can see that this sinusoidal pulse width modulation, unipolar switching. Okay, thank you very much for listening to all this video. You can share with your friends and let them also learn, and they can do a lot of other things here, like the triangular wave may be shifted right and left, and you can get analysis of that. Or the instead of having a sine wave, you can have a modulated sine wave with the fusing of some other harmonics in the sine wave, and then you can do the analysis of that. These things can be done in the research. Thank you.